Welcome to PhysicsNextbook. In this video, let us discuss the relativistic dispersion relation, that is, relation between the momentum of a relativistic particle and its energy. In the process, we shall discover the Hamiltonian and talk about its significance. The obvious first step is to compute both the momentum and energy using their most general definitions in terms of the Lagrangian and the velocity. Which Lagrangian? Of course, that of a relativistic free particle. It's this particle's energy and momentum that we are talking about, right? In our last video, we have seen how to arrive at the Lagrangian of such a particle. In an earlier one, we also established the definitions of energy and momentum for a generic mechanical system in terms of its Lagrangian. Both the videos are linked in the description in case you want to check on them. So we are all set. Okay, first the momentum vector, defined as the vector quantity whose components are conserved if the system has homogeneity of space as a symmetry, meaning the Lagrangian does not change from one location of space to the next, that is, independent of the space coordinates. This symmetry condition, in association with the generic form of the Lagrange's equation, gives us the mathematical formula to compute the momentum vector P of any mechanical system as del L del V. Do not get alarmed that we are taking derivative with respect to vectors here. It simply means taking partial derivative of the Lagrangian with respect to the components of the velocity one at a time will give us the corresponding components of the momentum vector. Now, the Lagrangian for the relativistic particle is minus mc squared, the rest mass energy, times the inverse of the Lorentz factor gamma. Gamma is given by inverse of the square root of 1 minus v squared upon c squared. So, the derivative gives us the constant minus mc squared as it is, times a half factor for the square root, then the square root itself goes to the denominator, and finally, the velocity derivative of the factor inside the square root, which is basically minus of twice the v vector upon c squared. The minus signs, the factor 2, and the c squareds cancel out. 1 upon the square root term is nothing but the Lorentz factor gamma, so the relativistic momentum vector is given by gamma m times the velocity vector. Some old relativity texts prefer to attach the gamma with the rest mass m and call it the relativistic mass or velocity dependent mass, so that the relativistic momentum formula mimics the non-relativistic mass times velocity form. But in a previous video, we have already discussed the problems with the concept of relativistic mass, so that's that. Going over to the energy of the relativistic particle, again defined as the quantity that remains conserved if the system has homogeneity of time. This is another symmetry which demands that the Lagrangian of the system does not depend explicitly on time. This condition and the Lagrange's equation together give the mathematical formula to compute energy as the scalar product of momentum and velocity vectors minus the Lagrangian. Now, to actually compute this for the relativistic free particle, we can either use the expression of relativistic momentum P to get energy as a function of the velocity, or we can try to invert the momentum-velocity relation to write velocity as a function of momentum to arrive at the relativistic energy-momentum relation directly. The first approach is straightforward algebraic simplification using the expression of the Lagrangian and then of gamma in terms of the particle velocity, and within a few trivial steps, it shows that the total energy is gamma times mc squared. This means the Lorentz factor times the rest mass energy is the total energy of a relativistic free particle. It's a remarkable result actually, because now we realize that the Lorentz factor gamma, which is originally defined as the ratio of coordinate time and proper time, is also the ratio of total energy and rest mass energy of the particle. Anyway, to find out how the total energy of the relativistic free particle relates to its momentum, the second approach is more useful, where we have to first invert the definition of momentum. Notice that because of the presence of gamma, which has velocity in it, it is quite a task to invert the relativistic momentum-velocity relation and express velocity in terms of the momentum. First, we need to use the definition of momentum to write gamma times the velocity vector as momentum vector upon the rest mass. Then we square the original expression of gamma and cross multiply to write gamma squared as 1 plus gamma v upon c whole squared. Now gamma v squared is nothing but the dot product of gamma times the velocity vector with itself. So we can replace that with p vector upon m dotted with itself, thus expressing gamma as square root of p squared plus m squared c squared divided by mc. This gives us gamma m, which we can use back in the definition of momentum to invert it and get the velocity vector. Now that we have the velocity completely in terms of the momentum, we can use it in the definition of energy. But for easier simplification, it would be prudent to write v as p upon gamma m in the first term and rewrite the minus of the Lagrangian, that is mc squared by gamma, in the second term as m squared c squared upon gamma m. Adding them up and then using the expression for gamma m, we get the total energy as c times the square root of p squared plus m squared c squared. The more popular version of this goes without the square root, simply expressing the square of the total energy as p squared c squared plus m squared c raised to the 4. This is the relativistic dispersion relation or the energy momentum relation. Let's check if it gives the energy of our non-relativistic free particle if we think of the low velocity scenario. Imposing the condition of low velocity means we assume v upon c, the speed of light, to be much less than 1. In this case, the Lorentz factor gamma becomes 1. So, the definition of momentum p equals gamma m times v becomes just p equals mv. Therefore, we can bring in the mass of the particle to rewrite the low velocity condition v upon c as p upon mc much less than 1. Making it suitable to use in the relativistic dispersion relation. Now, pulling the mc squared out, we can express the square root and retain only the first order in p upon mc whole squared. Ignoring the higher orders of p upon mc effectively means we have imposed the non-relativistic limit p by mc much less than 1 in our energy momentum relation. Simplifying, we get the non-relativistic dispersion relation, which says energy equals p squared upon 2m plus mc squared. Since in our non-relativistic limit p is just mv now, this is nothing but the familiar non-relativistic kinetic energy term half mv squared and the rest mass energy that we have seen in earlier videos. So we do have a consistent non-relativistic limit of our relativistic dispersion relation. Now, why is this dispersion relation so important? Because from the definition of momentum and energy, which are both in terms of velocity, the dispersion relation kicks out the velocity and connects energy directly to the momentum. When we replace velocity completely by momentum in the expression of energy, the energy is given a new name, the Hamiltonian. So the dispersion relations in relativistic and non-relativistic scenarios give us the corresponding Hamiltonians. But what does the Hamiltonian do? It paves the pathway to quantum theory. Let me explain. In quantum mechanics, we never think of velocity as an observable because velocity is nothing but local tangent vectors on the spacetime trajectory or world line of a point particle. And in quantum theory, the notion of a point particle gets mixed up with the notion of waves. There is this concept of wave-particle duality, which says that particles can sometimes behave as waves and vice versa. So, we cannot track the precise spacetime trajectory of a quantum mechanical particle. Therefore, observing the velocity of the particle is not an option in quantum mechanics. This is where it fundamentally differs with classical mechanics. That's why in most basic texts of quantum mechanics, you won't even see the Lagrangian of a system, which is a function of position and velocity. Rather, you will see the Hamiltonian. It is nothing but the energy of the system, but expressed not as a function of position and velocity, but as a function of position and momentum. And it plays a crucial role in computing the time evolution of a quantum mechanical system. Like in classical mechanics, where the time evolution of the system is decided by the force equation or the Lagrange's equation, which we solve to find the particle's position vector as a function of time, in quantum mechanics, there is this concept of a wave function psi, which describes the quantum state of a system and its time evolution is decided by the Hamiltonian of the system through the Schrodinger equation, which is written as IH cross times the partial time derivative of psi, that is del psi del t, equals Hamiltonian operating on psi. Now, to explain where does this equation come from, what do I mean by Hamiltonian operating on psi, why is there a I, which means square root of -1, an imaginary number sitting in front with the reduced Planck's constant h cross, we need to go way down the rabbit hole of quantum mechanics, which we are not going to do in this video. For the moment, just note that the del psi del t on the left is a measure of how the quantum state of the system changes with the passage of time, and on the right side, the Hamiltonian acting on the quantum state psi decides that. In fact, in classical mechanics also, the time evolution of the system can be worked out using the Hamiltonian. Like the Newtonian and Lagrangian mechanics, we have this whole scheme of Hamiltonian mechanics too in a classical scenario. But there, it is one of the alternative methods, whereas in quantum mechanics, using the Hamiltonian is the only straightforward way to track the time evolution. I hope you have got an idea of how the Hamiltonian works and what it does, and therefore can also appreciate why the dispersion relation is so very important. That's it for this video. Thanks for your time. See you in the next one. Bye-bye.